Hi, here we've got question 3 from the follow-up sheet that if you remember in class you asked me to do a little video of because I really wanted you to do it. So here we are, we're going to go through it now. Experiment 1, we've got a reaction going on here, calcium carbonate. I'm going through this reaction here. Calcium carbonate and hydrochloric acid gives us calcium chloride, water and carbon dioxide. When you do that reaction with 2.51 grams of calcium carbonate, you get a temperature drop of 4.5 degrees Celsius. So part 1 is calculate the energy change in joules for this reaction. Well, quickly, because I think you're good at these now. We're going to use Q equals mc delta T as usual, Q being heat, mass being the mass of the stuff that we're heating up, so that is the 50 cm cubed of hydrochloric acid. We're going to assume that's water, which has a density of 1. So 50 cm cubed has a mass of 50 grams. So we can put 50 in there. Specific heat capacity, we're also going to assume this HCl is water because mostly it is water. And the specific heat capacity of water is 4.18. And lastly, our delta T is given in the question as 4.5 degrees C. So our Q is going to be the product of those three numbers, which I think comes out at 940.5. And that's in joules. It's in joules because we've got grams here. So that's our answer to part 1. Quite straightforward. So let's move on to part 2. So we'll do part 2 here. Part 2 is the amount of moles of calcium carbonate. So we're going to use N equals M over Mr, where Mr of calcium carbonate. So where it's asking us for calcium carbonate, the Mr of calcium carbonate is going to be 1 calcium plus 1 carbon plus 3 oxygens, 3/16 of 48. So I think that gives us about 100, 100.1 is the Mr of calcium carbonate. And our M is given in the question 2.51 grams. And so the number of moles of calcium carbonate, let's put our calcium carbonate in brackets there. Our number of moles is 2.51 divided by our 100.1, and that comes out at 0.0251. 0.0251 moles of calcium carbonate. And so that's our answer to part 2. Moving straight on to part 3. Calculate the amount in moles of hydrochloric acid this time. So part 3, we're going to use a new equation again. So there's 3 equations. So we've got concentration equals moles over volume. So we're just going to rearrange that. So moles equals concentration times volume, where our concentration must be given in the question. Looks like it's 2. So our concentration is 2 moles per dm cubed. And our volume is 50 cm cubed. But again, of course, we need to change our units into decimeters cubed. So we're going to divide that by 1,000. And so that means our moles of hydrochloric acid is coming up at 0.1. So we've got 0.1 moles. So I'm just going to underline that in red and underline that in red, because that's going to help us with the next question. So we've done that one as well. So part 4, which reactant is in excess and which is the limiting reagent? Well, the one that's in excess is the one that there is most of. That's the definition of a reactant being in excess. So 0.1 is a lot bigger than 0.0251. So our hydrochloric acid is in excess, which leaves the limiting reagent as our calcium carbonate. So let's just dwell on that term limiting reagent. All right, so a reagent is just a reactant, In this case it's calcium carbonate, but it's described as the limiting reagent because there is less of it. There is less of it than the hydrochloric acid. So that is what limits the amount of product that you're going to get. So if you've got 0.0251 moles of calcium carbonate, you can't make more than 0.0251 moles of our product, which is calcium chloride. So that is the reagent that limits the amount of product that you can make, and that's why we call it the limiting reagent. So that's that one answered. And lastly, part 5, calculate the enthalpy change in kilojoules for the reaction of 1 mole of calcium carbonate. So we're going to call this now our delta H, and that is equivalent to Q over N. And our Q we worked out in part 1, which is up here, which was 940.5 joules still. And our N is the moles of calcium carbonate, which we worked out in part 2, which is here, which is 0.0251. Okay, so we're still in joules so far, but let's carry on. So this sum here comes out at 37,478 joules, like we said. It's joules, and it's per mole now because we divided by the 0.0251, and we can quickly convert that into kilojoules by dividing by 1,000. So it's 37. Let's call it 37.5 kilojoules per mole, like that. And so that is the answer to question 5. I think let's just answer. So we were required to give it to 3 significant figures, 1, 2, 3. So we're all done for this part of the question. And let's quickly go through experiment 2. So the student carried out an experiment to find the enthalpy of a reaction when calcium oxide reacts with dilute hydrochloric acid. That's another way of getting calcium chloride. And we've got to go through the same process. So let's do that quickly. Part 1 is going to be calculating the energy change in joules for this reaction. So we're going to use our Q equals mc delta T again, where our M is 50, our C is 4.18, and our delta T this time is an increase of 6. So those 3 multiplied together come out at 3,344 joules. So that's quickly done part 1. Part 2, calculate the amount in moles of calcium oxide. So part 2, moles of calcium oxide is going to be the mass of calcium oxide divided by the MR of calcium oxide, where the mass is given in the question, here 1.42 grams, and the MR of calcium oxide is going to be calcium, which is 40 plus 16, which I'll make 56, and so 1.4 over 56 is going to come out at 0.0253. So that's how many moles of calcium oxide we've got. Part 2. Part 3, swiftly, we've got calculate the amount in moles of HCl. So in the same way, we're going to use concentration equals moles over volume, rearranged to give us moles equals concentration times volume, where concentration is probably given in the question. There it is, 2 molar again. So we're going to have 2 moles of that, and our volume is 50 again. And like before, we're going to convert it into litres, decimeters cubed by dividing by 1,000. And so that comes out as before at 0.1 moles of HCl. So there we are, quickly done part 3. Moving on to part 4, which reactant is in excess. So in the same way, our hydrochloric acid is in excess because we have 0.1 moles of it, whereas we only have 0.0253 moles of calcium oxide. So that's the answer to part 4. And quickly part 5, calculate the enthalpy change in kilojoules. Okay, so that is the same calculation. Delta H equals Q over N, where Q was 3344 from the first part of the question, and N, it's the N of calcium oxide, so that's our 0.0253, and so that comes out at 132.1733. So that is actually 1,321,733 joules. But it's a temperature decrease, isn't it? It's a temperature increase. So it's an exothermic reaction, so we're going to have to put a minus in here. And then we're going to also turn it into kilojoules. So dividing it by 1,000, so that's going to be 132 kilojoules. Something's gone wrong with the decimal places there. So I think it's probably like that. Anyway, the answer is 132 kilojoules per mole, like that, to 3 significant figures. So again, that's that one done for the second reaction. And now I think is the interesting part of the question here. So let's move on to that. So here's the interesting part of the question. So we have to draw an energy cycle or a thermocycle, linking the experimental values, that's the values that we've just calculated in parts A and B, to the thermal decomposition of calcium carbonate, and use it to calculate the enthalpy change for the following reaction. So let's call that delta HR. That's the enthalpy change we're required to calculate. So let's just pause and reflect on what we've done. In experiment 1, we took calcium carbonate here, and we reacted it with hydrochloric acid to get calcium chloride. In experiment 2, we took calcium oxide and reacted that also with hydrochloric acid, and we got calcium chloride. So in both cases we have taken these two, calcium carbonate and calcium oxide, reacted both of them with hydrochloric acid and got the same product, calcium chloride, in both cases. And so with that information we can therefore find the third point of the triangle. So here we go. What I will do is I'll write out the original reaction above. A little bit repetitive, but let's be ultra clear about this. So we're taking some calcium carbonate, and this reaction is just a thermal decomposition reaction. It's the limestone reaction we did at GCSE. There it is. And what we're going to do is we're going to make the third point of the triangle down here. We're going to make those the products of the two reactions, which were the same in both cases. So I'm going to leave a space like that. Hopefully I'll be able to fit all those products into that space. So the first reaction we did in experiment 1, that is going to represent this arrow, and the second reaction is going to represent that arrow there. So in the first experiment we took calcium carbonate and we added some hydrochloric acid to it. Alright, so we're going to add that hydrochloric acid, and didn't we add, the balanced equation was +2 moles of hydrochloric acid. And when we did that, we got calcium chloride, and we also got water, and we got carbon dioxide. They were the products from the first reaction. Now let's remind ourselves of the second reaction. Didn't we take calcium oxide this time, and we also added 2 moles of hydrochloric acid? And when we did that, we got calcium chloride again, and we got some water. We didn't get any carbon dioxide, but you can see the carbon dioxide was in here and it appears here as well, so that's going to cancel out. So that's the crux of the question, and I'll just repeat it again for clarity. So we've got a reaction for which we want to calculate the enthalpy change, and we've done two experiments, both producing the same products, in this case with the same other reactant, hydrochloric acid. And when that's the case, you can draw a thermocycle that looks just like this. And the direction of the arrows just go from reactants to products. So in the first reaction, calcium carbonate was our reactant, and so our arrow goes from calcium carbonate to our products of the first reaction, calcium chloride, water and carbon dioxide. And in the second reaction, our calcium oxide was our reactant, and so the arrow goes from calcium oxide to the same product. That explains the direction of the arrows as well. And now what we can do is we can add in the enthalpy changes that we calculated earlier on. So this one was plus 37.5. That was an endothermic reaction. The temperature went down. And the second one was an exothermic reaction. It was minus 132, I seem to remember, kilojoules per mole. And we've got 1 mole of calcium oxide and 1 mole of calcium carbonate. So it's just one multiple of the 37.5 and the 132. So now we've added in the two experimental enthalpy changes, and now it's just a matter of calculating delta HR. So let's switch back to blue, right down here. Delta HR, the one that we're interested in, is going to go around the alternative route. So we're going to go around in this direction. So we are going with the first arrow, and so we are going to keep the sign of the 37.5, but we're going against the arrow of the second reaction, so that's going to be a minus 132, like that. And so our enthalpy change is going to be plus 170 kilojoules per mole, and that's the answer to part C. Okay, last part D is interesting again, slightly different. So using the additional data below, that's this data and this data, and our calculated value for the thermal decomposition of calcium carbonate. So if you remember from the previous slide, that was 170 kilojoules per mole. And what they want us to do is to calculate the enthalpy of formation of calcium carbonate. So that's delta HF of calcium carbonate, which is what we started off with. And it gives you that data there. So you can do that in two ways. You can do this question with a thermocycle. That's the way I prefer to do it. You can also do it with a formula, which is a little bit quicker, a little bit less intuitive. I'll show you that way as well. So first of all, with a thermocycle. First thing we're going to do is write out our equation. Now we're trying to work out enthalpy of formation of calcium carbonate, but we're using the first original equation. So we've got calcium carbonate, if you remember, and we're thermally decomposing that into calcium oxide. And giving off some carbon dioxide there. And so let's write it in this order here, where we're forming first of all the calcium carbonate, and secondly the calcium oxide. So if we're forming it, we're going to put the elements down at the bottom, in the bottom point of the triangle. So we're going to have some calcium down there, we're going to have some carbon, and we're going to have some oxygen. We need 3 atoms of oxygen, but at standard state oxygen exists as a diatomic molecule. So that means we're going to have 3/2 moles of oxygen 2, gives us 3 atoms. So with those 3 elements in those quantities, we can make our calcium carbonate, our 1 mole of calcium carbonate. And we can also make our 2 products of the top reaction. We can make 1 mole of calcium oxide and we can make 1 mole of carbon dioxide. So that's our diagram, and it's a formation diagram. So you notice the arrows are going from the elements to first the reactant, calcium carbonate, and secondly the products, calcium oxide and carbon dioxide. So now we can put in our values. Our 170 is going to go in here. It's an endothermic 170. And let's do this one now. This is the one we don't know. This is the one the question's asking us for. So this is the enthalpy change of formation of calcium carbonate. And the third leg of the triangle, we're going to use this new data here and here to make up that. So you can see that we're forming 2 things in this leg. We're forming 1 mole of calcium oxide and we're forming 1 mole of carbon dioxide. We've got all of our elements down at the bottom there, and so it's simply just a case of adding the 2 enthalpies of formation. And so we've got for carbon dioxide, we've got -394, and for calcium oxide we have -635, and we're going to add those together, and that gives us -1029 kilojoules per mole. That's to make 1 mole of calcium oxide and 1 mole of carbon dioxide. Now we have everything that we need, so we just need to appreciate that in order to calculate the enthalpy change of formation of calcium carbonate, we're going to go around the enthalpy cycle in that direction. So we're going with the first arrow, we're going with this arrow here, so we can keep those numbers the same. So delta HF is going to be our -1029. Now we're going against the arrow, the top arrow. We're going against that arrow there, so we have to turn the 170 into -170. And so the total enthalpy of formation of calcium carbonate works out to be -1199 kilojoules per mole. Like that. That's the answer. It can also be done with a little formula that requires you to remember it. The reason why I like doing a thermocycle is because I can work it all out from first principles, and it saves me remembering the formula. But in case you like remembering formulas, we'll do that way as well. So I'll do that in green. And so our delta H formation of our calcium carbonate is just going to be our delta H formation of our products minus the delta H formation of our reactants. Where these are our products, so we can substitute in those values there. So we've got, in the same way, we've got our -1029 minus our delta H of our reactants. This is our reactant, and so it's minus a positive 170, and so it comes out at exactly the same number, of course, -1199 kilojoules per mole. So a bit quicker, you can see, to do it the second way with the equation, but it does require you to remember this equation. So up to you which way you work it out.